Okay, well, we're going to talk today a little bit about volume ventilation and looking at a pressure time scaler. So what I've drawn so far is I have a pressure on this axis, which obviously starts at 0 and then increases as we go up, and then the time on the other axis, which obviously starts at 0 and goes up this way. So when you look at volume ventilation, and for this example, we're going to explain that we have a 500 milliliter breath, and we're going to be pushing that breath in at 60 liters per minute. Okay? When that breath starts to go in, you're going to see on this pressure time scaler the baseline pressure, which in this example we're going to call a baseline pressure of 5 centimeters of pressure, which obviously is your PEEP level. You'll see that pressure level increase because the ventilator is actually fighting against two different aspects to push that 500 milliliters into the patient's lungs. The very peak of the breath, or the peak of the pressure, is actually called the peak inspiratory pressure, also known as the peak airway pressure by some authors. Now, normally, if we were to let that breath come back out, we would just see this pressure time scaler come back down to the PEEP level. And if we looked at that, we would say to ourselves, well, it took this much pressure, and in this example, I'm going to imagine that that peak inspiratory pressure is 55 centimeters of pressure, to overcome the resistance and the compliance of the patient. But it really doesn't separate out how much pressure was used to overcome the compliance and how much pressure was used to overcome the airway resistance. To figure that out, you have to place an inspiratory pause on the patient's ventilator. And when you do that, you'll see that the pressure, after going up to a peak inspiratory pressure, will come down and hold at a horizontal line. This is known as your plateau pressure, and once again, it's taken by instituting an inspiratory pause on the ventilator. And then obviously when the inspiratory pause is done, that pressure will drop back down to the PEEP level. Okay? This pressure over here is still at 5 centimeters of pressure. Okay? So the PEEP level that you see over here is the same PEEP level over there. So, why is this plateau pressure so important in volume ventilation? Well, without the plateau pressure, we can't tell how much of this peak inspiratory pressure was due to airway resistance and how much of this peak inspiratory pressure was due to static compliance. With the plateau pressure, in this example, we're going to imagine that plateau pressure was 25 centimeters of pressure. With that plateau pressure there, now we get two very distinct different parts of this pressure time scaler. The first part we're going to see is going to be the difference between the peak inspiratory pressure and the plateau pressure, represented here by the little green hash marks. Okay? This part of the pressure time scaler is going to be the pressure used to overcome airway resistance. Now, students get confused very often because I'll say, this is the pressure used to overcome airway resistance, and they'll start saying, well, 55 minus 25 is going to be your airway resistance. And I say, no. 55 minus 25 was how much pressure it was required to push past all the airway resistance. It demonstrates the pressure needed to overcome the airway resistance. So when I write this in, you'll see that I'll write this overcomes airway resistance, or resistance in the airway. Okay, it's the pressure used to overcome the resistance in the airway. Now the second part of this pressure time scaler is obviously from my PEEP level up to my plateau pressure, okay, which is going to be this part of the graph. This part of the graph, we didn't have any flow anymore, which is why we had that inspiratory pause. The breath was going in, the breath was delivered here, and then we held the gas in for a second, so there was no more flow, and therefore no more airway resistance. Since there's no airway resistance, because there's no turbulence, because there's no flow, the pressure dropped from 55 down to 25, and then it stayed there until the end of my inspiratory pause. Now, that pressure here is due only to the compliance of the patient's lungs. So before, when the breath was going in, we had flow, which was either streamlined or turbulent, depending upon a lot of different factors described by Reynolds. And we also had pressure due to this alveoli stretching with the breath. Okay? Now this is only one alveoli and one terminal bronchiole, but understand that this represents all of the tubes, both artificial and anatomical, in the patient's lungs, and this one alveoli represents, all of the lungs, or all of the alveoli. And although I've made the arrows pushing apart, showing the alveoli is opening up, imagine that there's pressure being generated back here because that alveoli doesn't want to continue to stretch. So, from baseline to the peak inspiratory pressure, we had both of these things occurring. Once we got to the peak inspiratory pressure and we held the breath, we now removed all of the flow, and the only pressure that we have left coming back from my patient is pressure due to the patient's compliance. Okay? Since this compliance is measured under no gas flow, this is called static compliance. So when we look at this graph and we say, well, the difference between the plateau pressure and the peak, why is that pressure gradient there? It's because that pressure is required to push this volume in against this patient's static compliance. Or it's the pressure used to overcome static compliance, abbreviated big C, little s. The last concept here to cover is the concept of dynamic compliance, in which authors describe the total pressure change per total volume change, or change in volume over change in pressure. Dynamic compliance is the difference between the peak inspiratory pressure and the plateau pressure. Therefore, the difference between the peak inspiratory pressure and the plateau pressure is the pressure used to overcome dynamic compliance, big C, dyn.